Let f of x and g of x be real-valued functions on the real numbers. Part A. Write down the conditions that f of x and g of x must satisfy if they are to be mutually tangent when x equals x sub 0. For f of x and g of x to be mutually tangent at x sub 0 along this line, it's clear that f of x and g of x must meet. They must have the same value at x sub 0. So we must have that f of x sub 0 equals g of x sub 0. So the first condition is that f of x sub 0 equals g of x sub 0. In addition, we must have that at x sub 0, the gradient of f of x and g of x are equal, i.e. we must have that f dashed of x sub 0 equals g dashed of x sub 0. And so the second condition is that f dashed of x sub 0 equals g dashed of x sub 0. And so we have that f of x and g of x are mutually tangent at x equals x sub 0 is equivalent to the two statements f of x sub 0 equals g of x sub 0 and f dashed of x sub 0 equals g dashed of x sub 0. Now let f of x equals the log of h of x all to the power p, g of x equals k times h of x, with p and k being real numbers, and let a point of mutual tangency, p, of f of x and g of x occur when x equals x sub 0. Part B. Find the possible values of h of x sub 0 and k at p. So we let the point of mutual tangency be p with coordinates x sub 0, y sub 0, and from part A we require f of x sub 0 equals g of x sub 0, f dashed of x sub 0 equals g dashed of x sub 0, and we label those statements 1 and 2. And so from 1 we have that the log of h of x sub 0 to the power p must equal k times h of x sub 0, and we call that statement star, and we note in passing that this tells us that h of x sub 0 cannot be equal to 0, because otherwise the left-hand side would be undefined due to the fact that we take the log of h of x sub 0. Now we have that f of x equals the log of h of x all to the power p, and that tells us, if we apply the chain rule, that f dashed of x equals p times the log of h of x to the p minus 1 times the derivative of log h of x. And on applying the chain rule to the derivative of log h of x, we find that f dashed of x equals p times the log of h of x to the p minus 1 times h dashed of x over h of x. And that's an important result, so we put it in a blue box. Also, since g of x equals k times h of x, then we have that g dashed of x equals k times h dashed of x. And that's another important result which we put in another blue box. And so applying those results, 2 tells us that p times the log of h of x sub 0 to the p minus 1 times h dashed of x sub 0 over h of x sub 0 equals k times h dashed of x sub 0. And we can rearrange that, factor out the h dashed of x sub 0 to find that h dashed of x sub 0 equals 0, or p times the log of h of x sub 0 to the p minus 1 over h of x sub 0 minus k equals 0. And first we look at the statement h dashed of x sub 0 equals 0. If we look at f dashed of x, we see that it has a factor h dashed of x, and similarly for g dashed of x. And hence, if h dashed of x sub 0 equals 0, then f dashed of x sub 0 and g dashed of x sub 0 also equals 0. And so in this case, we see that we have no restriction on h of x sub 0, since h dashed of x sub 0 equals 0 tells us nothing about h of x sub 0. And we also have no restriction on k, since the equation 0 equals k sub 0, which comes from g dashed of x equals k times h dashed of x, is satisfied for all real k. And now we consider the second condition, and on multiplying through by h of x sub 0 and rearranging, we have that p times the log of h of x sub 0 to the p minus 1 minus k times h of x sub 0 equals 0. But the k times h of x sub 0 term from the statement that we called star is equal to the log of h of x sub 0 to the p, and so we have that p times the log of h of x sub 0 to the p minus 1 minus the log of h of x sub 0 to the p equals 0. And from that we can factor out log of h of x sub 0 to the p minus 1 to give us the log of h of x sub 0 to the p minus 1 times p minus the log of h of x sub 0 equals 0, from which we get the conditions the log of h of x sub 0 to the p minus 1 equals 0, or p minus the log of h of x sub 0 equals 0. And we look at the condition on the left first, log of h of x sub 0 to the p minus 1 equals 0. So if we have that log of h of x sub 0 to the p minus 1 equals 0, then we must have that the log of h of x sub 0 equals 0, which gives h of x sub 0 equals e to the 0, which equals 1. And then we bear in mind the relationship star, that the log of h of x sub 0 to the p equals k times h of x sub 0. Log of h of x sub 0 is 0, h of x sub 0 is 1, so we have 0 to the p from the relationship star equals k times 1, which gives k equals 0. And we know that g of x equals k times h of x, so in this case we have g of x equals 0 times h of x, which equals 0. So in this particular case, g of x is the 0 function. And so here we have one solution, h of x sub 0 equals 1 with associated value k equals 0. But earlier we derived the following result for f dashed of x sub 0, and noting that the log of h of x sub 0 equals 0 in this case, which appears here in the formula for f dashed of x sub 0, we see that f dashed of x sub 0 equals 0 in this case. And so we have a trivial solution with g of x being the 0 function and f of x having a turning point on the x-axis. And we now consider the other condition, p minus the log of h of x sub 0 equals 0. And so we have that the log of h of x sub 0 equals p, so that h of x sub 0 equals e to the p. Bearing in mind the relationship star, we can write k equals the log of h of x sub 0 to the p over h of x sub 0, which gives us p to the p over e to the p, and we have finally h of x sub 0 equals e to the p with associated value k equals p over e to the power p. And so in the blue boxes we have the two possible values of h of x sub 0 and their associated values of k. The functions 3 times the square of the log of x plus 2 log x and lx cubed minus 1/3 have a mutual tangent for some real L. Part C. Find the value of L and the coordinates of the point of intersection of these functions. In Part B, we found two possible sets of values for h of x sub 0 and k at p, the point of mutual tangency. One of those sets of values was only valid when g of x was the 0 function, and clearly that is not the case in this question. We have to use the result that if f of x and g of x have a point of mutual tangency at x equals x sub 0, then h of x sub 0 equals e to the p and k equals p over e to the p. But we see that the functions in this question are not in the required form because we need the same function here in g of x and here in f of x. And so we have to transform the provided functions into the required form, which is presumably possible. And so we will call the function involving the log of x r of x and the function involving x cubed s of x. And we can immediately note that r of x looks rather like a quadratic expansion, but it's lacking a constant. And we can also note that the constant in s of x doesn't work with log functions particularly nicely. And we have to bear in mind that we need to produce the same function in both s of x, or a variant of it, and r of x. So constants that don't work nicely with log functions are not what we need. And we can see that what we want to do, apparently, is to add some constant to r of x and remove one from s of x. We can do both of those things at the same time if we bear in mind that we are interested in a point of mutual tangency, because a point of mutual tangency between two functions will still exist if we shift both of the functions up or down the y-axis by the same amount, which in this case is clearly plus 1/3. And so we construct two new functions, r1 of x, which equals r of x plus 1/3, and s1 of x, which equals s of x plus 1/3. And we note immediately that we have a constant 1/3, which is slightly unpleasant. The obvious thing to do is to turn it into an integer. So can we turn it into an integer? Well, yes, we can, if we note the following fact, that if we have two functions p and q that share a common tangent, then if we multiply both of those functions by a constant c, the new functions still share a common tangent. And so we construct r2 of x, which equals 3 times r1 of x, and s2 of x, which equals 3 times s1 of x. And r2 of x becomes 9 times the square of log x plus 6 log x plus 1. s2 of x becomes 3l times x cubed. And from the observation that we made here, we can be sure that r2 of x and s2 of x also share a common tangent. And we immediately see that r2 of x equals 3 log of x plus 1 all squared. But these two functions are not yet in the required form because we want functions that look like log of h of x to the power p and k times h of x, where h of x appears in both functions. Now we can rewrite r2 of x. We note that 3 log x equals the log of x cubed and 1 equals the log of e, and we can combine those two terms into the log of ex cubed, and so we find that r2 of x equals the square of the log of ex cubed. And we can see that in order to write the functions in the form in the blue box, we will need h of x equals ex cubed and k times h of x equals 3l x cubed, which gives, after a little working, that k equals 3l over e, so that l equals ke over 3. And now we have two functions in the required form. We have f of x and g of x, with h of x being ex cubed, p being 2, and l being ke over 3. And so we can apply the result from part B. And that tells us that h of x sub 0 equals e to the p, which here equals e squared, giving e times x sub 0 cubed equals e squared by substituting for the formula for h of x. And that tells us that x sub 0 equals the cube root of e, or e to the power 1/3. and we can find the y-coordinate corresponding to x sub 0. Y sub 0 equals r of x sub 0, which equals 3 times the log of x sub 0 all squared plus 2 log of x sub 0, which becomes 1. Now that gives us the coordinates of the point of mutual tangency, but we also require the value of L. We know that k equals p over e to the power p from part B, and here that becomes 4 over e squared. And so L, which is ke over 3, becomes 4 over 3e. And so finally we have that L equals 4 over 3e, and the coordinates of the point of mutual tangency P are e to the power 1/3 and 1. And here we have a graph of the two functions showing the point P of mutual tangency. Please note that the axes are not to the same scale. R of x is the curve in red, S of x is the curve in blue.